In this segment, we're going to start talking about Cmos logic design. So the first thing to do is to say that Cmos stands for Complementary MOS. And this refers to the fact we have both N-type and P-type transistors that we can make on the same in the same circuit, on the same chip. And hopefully you'll have a better sense for how that comes about in terms of fabrication and technology by having watched the Silicon Light video, which I'm suggesting that you take a look at this week. It has some really nice animations about how these things are fabricated and how they work in the context of digital logic anyway. And so we're going to start out by thinking about something called conduction conditions. For networks of transistors. Okay, these are Boolean conditions under which a network of transistors connects the two ends of the network. Okay, so suppose we have a single NMOS transistor. That's our network. We've got some Boolean signal A into the gate, and we have X and Y on either side. So X and Y are connected if A. So if A is true, that means X and Y will be connected by a low impedance path. And if A is false, then X and Y will be disconnected. Okay, if A is high, that means that the transistor will be above threshold, and X and Y will be effectively shorted together. If we want to think of the transistor like a switch, that makes the switch closed, and X and Y are connected together. However, if A is at 0, at ground, then X and Y will be disconnected from each other. The transistor will be as off as we can make it by putting voltage on the gate in between the power supply rails, and so X and Y will be disconnected. The transistor will be in weak inversion or subthreshold and as off as we can make it. Okay, so how about if we put two NMOS transistors in parallel with each other? Like so. We have X over here and Y over here. And let's say we have A up there in the gate of the top transistor and B down here in the gate of the bottom transistor. Well, if A is high, then clearly if I had a conducting path down here, then I'll have a conducting path up here. Alternatively, if B is high, I'll have a conducting path through the B transistor. And if both of these are on, then I will have a conducting path that's even a little bit stronger than if only one of the two are on. So if we have these two transistors here in parallel, then we have conduction if either we have conduction through one of them, or if we have conduction through the other one, or if we have conduction through both. And so that corresponds to the logical operation of disjunction or logical OR. So here, X and Y are connected if A or B. So the notation we're going to be using is very typical for what you'll probably see in computer architecture, where here plus means disjunction or logical OR. Okay, so the parallel configuration corresponds here to disjunction. So A or B would be the conduction condition for this configuration, two NMOS transistors in parallel. And for this particular configuration of a single NMOS transistor, the conduction condition is just A. Okay, it's a Boolean condition that corresponds, the truth of which corresponds to conduction in the network of switches or transistors. Well, how about something like two NMOS transistors connected in series? So we have X over here and Y over here, and we'll have A in the gate of this one and B in the gate of this one. Well, here X and Y are connected. Well, in this case, with a series configuration, if either of these two switches are off or open, then we can't get conduction through this network. We have to have both the A switch conducting and the B switch conducting in order for us to have conduction through the series combination. So here, the series connection would correspond to conjunction, or logical and. And we denote this, again, in this sort of common Boolean algebra notation by multiplication. So we won't often put a dot, an explicit dot, in our Boolean expressions here, but just to let you know that the multiplication, or just the juxtaposition of A and B, corresponds to logical and in our notation here. So we have parallel corresponding to or, and series corresponding to and. So parallel corresponds to disjunction, and series corresponds to conjunction, or and. So this is an important observation from what we've seen so far. What about for a Pmos transistor? Let's suppose we have a Pmos transistor here. Well, in order to turn the Pmos transistor on, we have to make the gate low. Right? So Pmos transistors get turned on harder the lower we make the gate voltage. So if we make A 0, or logical false, which is typically represented by ground, then we will be turning this transistor on as much as we can by applying a voltage between the power supply rails. And so that would correspond, or actually, let me say, if we were to make A logical 1, which is represented typically by VDD, the positive supply voltage, this transistor would be in weak inversion and the switch would be off. As off as we can make it, again, by putting a voltage on the gate within the power supply rails. And so here, X and Y are connected. If not A. So the over bar is what we're going to be used for. What we're going to be using for not. Okay, so the bubble on the gate corresponds to complementation of the Boolean that's applied to the gate. What about two Pmos transistors in parallel with each other? Well, here again, we're going to get conduction between x and y if we have conduction through the A path, or we have conduction through the B path, or we have conduction through both paths. And so here, x and y are going to be connected. If not A or not B. And so here we have the parallel configuration of the switches corresponding here to disjunction, or logical OR, and the bubbles on the gates correspond to having each of these Boolean variables or inputs negated. And by one of De Morgan's laws, we can write this as, which is, this is equivalent to not A and B, A NAND B. Right, so one of De Morgan's laws basically says you can take these overbars up one level and change disjunction to conjunction, and so this becomes A NAND B. Okay. What about the series configuration? And here we can cheat a little bit. Series configuration of two Pmos transistors. Well, just like with the Nmos transistors, we're only going to get conduction through the series pair if we have conduction through both, because either one of them can block the conduction in the series configuration. So x and y connected if not A and not B, which by De Morgan's other law would be A nor B. Okay, so again we pop the overbar up one level and we change the conjunction to disjunction in De Morgan's laws. So here we have nor. Okay, so again we have three basic ideas. So series corresponds to and, parallel corresponds to or, and if you have a bubble on the gate, that corresponds to putting a not on the Boolean variable that gates the Pmos transistor, or that's going into the gate of the Pmos transistor. Okay, so more generally, if I had, let's say, two networks, let's say I have a network here whose conduction condition, let's say, is represented by, I don't know, F. So that this network, these two sides of this network are connected only if F is true. And we have another one here which is conducting if G is true, and we connect these two networks in parallel with each other. Here X and Y will be connected if F or G. Right, because I can have, if F is true, then I get conduction through the F network. If G is true, I get conduction through the G network. And if F is true and G is true, I get conduction through both networks. And so that corresponds in terms of conduction conditions to F or G. Okay? And if I have the series connection with these same two networks, I've got two networks F and G that are connected in sort of cascade with each other, or in series. Here X and Y are connected. If I have conduction through both, only through both. So if F and G. Okay? So that's kind of a generalization of the parallel corresponding to disjunction and the series connection corresponding to conjunction. So here the F box and the G box could be several transistors connected in series or in parallel or something like that, and they each have their own little conduction condition. To get the conduction condition of the composition of these two through the parallel configuration, we would take the expression that corresponds to the conduction condition for the F network and OR it with the conduction condition for the G network. Here we would take the F network conduction conditions and AND it with the G network conduction conditions to get the overall conduction conditions of the series combination. Okay, that's the basic idea. Okay, so how do we take these ideas and make a basic Cmos logic gate out of it? So we're going to be looking at a very basic Cmos logic family called static, complementary, Cmos, or fully complementary Cmos. Now, the static. So the basic idea is that we have here two networks. This one is called the PUN and the PDN. And the output of the gate here is in the middle, between the node between the pull-up network PUN and the pull-down network PDN. And we have a bunch of inputs, A, B, C, that go into the pull-up network and also into the pull-down network. And let me see, PUN is the, said it several times here, the pull-up network. And here the PDN is the pull-down network. And the job of the pull-up network is to pull the output of the gate up to VDD. The pull-down network's job in life is to pull the output of the gate down to ground. Okay, so the pull-up network is responsible for producing the logical high values for the gate, and the pull-down network is responsible for producing the logic low levels for the gate. And A, B, and C here represent the inputs to the gate. There could, of course, be more than 3 or less than 3. And then usually you'll find all of the inputs supplied to the pull-up network are also supplied to the pull-down network. So the pull-up network pulls the output high by making a nice low impedance conduction path between VDD and the output. The pull-down network pulls the output down to ground by producing a nice low conduction or low impedance path between the output and ground. Okay, so let's say that the pull-up network conduction condition is represented by the pull-up network is U for up, and the conduction for the pull-down network is D. Okay, so U is the conduction condition for the pull-up network, and D is the conduction condition for the pull-down network. So if U or D is equal to 1, if that's true, if U or D is true, then gate is combinational. Okay, that's just a definition. So we talk about combinational logic gates, and a gate is combinational if there is no condition of the inputs. This condition here basically says there is no condition, no state of the inputs that we're applying to the gate where the pull-up network is not conducting and the pull-down network is not conducting. Okay, so you either have the pull-up network conducting or the pull-down network conducting under all circumstances. That's maybe the better way of saying it. Here the gate's output is either is connected low or high for all combinations of the inputs. Okay. If U or D is not 1, the gate is state holding. Okay, that basically means that there are some conditions on the inputs, or some combinations of the inputs, where the output is not driven high by the pull-up network, and it's also not being driven low by the pull-down network, and so it has to maintain its state somehow. Okay, that's what state holding means. So there are some sort of conditions or combinations of inputs where the output is not being driven by the pull-up network or the pull-down network. In other words, they're both disconnected. The other thing we'll say about this is that we basically must have that U and D is false. What does that mean? That means we never want So we don't want a situation where both the pulled up network and the pulled down network are both conducting at the same time. What that leads to is a short between VDD and ground. So that leads to power consumption. This is sometimes called crowbar current. Or shoot through. So basically, we don't want to have a situation where the pull-up network is conducting at the same time as the pull-down network is conducting for any substantial period of time. Sometimes you'll have a situation where the pull-up network is sort of going from on to off, and the pull-down network is going from off to on, and there'll be some sort of transient period of time where they're both conducting at the same time. And that can lead to a transient little blip of current, but we don't want a sustained condition where they are both conducting. Okay, so that's a couple of things. There's definitions of combinational gates and state-holding gates. We'll see some examples of both types of gates, and this idea that we want to design our gates in such a way that we never have the conduction of the pull-up network at the same time as the pull-down network. Okay, some other considerations. We make pull-up network out of Pmos transistors. And we make the pull-down network out of Nmos transistors. On the post lab, you're going to be considering, for post lab 5, you're going to be considering why that discipline why that design discipline is the case. So we exclusively use Pmos transistors for the pull-up network, and we only use Nmos transistors for the pull-down network. We never pull up with an Nmos transistor, and we never pull down with a Pmos transistor. And like I said, on post lab 5, you'll be considering why we put that restriction on ourselves when we design logic gates out of Cmos transistors. Okay. So with that in mind, let's look at our first logic gate. The simplest of all logic gates. And that is where the pull-up network comprises a single Pmos transistor, and the pull-down network comprises a single Nmos transistor. Okay, so let's think about this. So if A, let's make a truth table. There's only two possibilities for A, 0 or 1. And let's make A 0. Well, what do we know about the Nmos transistor? Well, if we make A 0, connect the gate to ground, the Nmos transistor is going to be off, down in weak inversion. And the Pmos transistor, meanwhile, is going to have the source up at 5 and the gate down at ground. So it's going to be as on as we can make it. It's going to be way up in strong inversion. And so we're going to have a nice solid conducting path between VDD and Y. So the output Y is going to be a 1. On the other hand, if we make a 1, tie A to VDD, then the Nmos transistor, which has its source at ground, will have its gate up at 5 volts, or whatever VDD happens to be, making that transistor on as far as we can make it. And then the Pmos transistor, which has its source up at VDD and its gate up at VDD, will be off as we can make it. And we have a nice solid connection between the output of the gate and ground. And so the output will be pulled low to ground. And so this is the function y equals not A. And so this is a Cmos inverter. And we typically will show this in our logic sort of circuit schematics using a symbol that looks like this, where this is the input A and this is the output Y. So this is the schematic, truth table, Boolean expression. This is the logic symbol. All right, that's going to be where we stop right now. We'll consider some more concrete examples of logic gates, and we'll talk about how to synthesize logic gates from Boolean expressions and how to read the Boolean expressions off of the schematic of the logic gate at the transistor level next time. See you then.